Hello, student. Welcome back to this topic of analog to digital converters. And in the last class, I have explained different kinds of ADCs, and also we have seen the advantages and disadvantages of each ADC. And the need for the design of different kinds of ADC is that one needs an ADC with low conversion time. So conversion time is an important factor that has to be taken care while designing or while selecting an ADC. The conversion time means how much of time is taken by the circuit to convert an analog signal into a digital signal. That is called as the conversion time. And different kinds of ADCs have different conversion times, and some ADCs have low conversion time, but some other ADCs have high conversion time, or they take a long time for to convert analog signal into a digital signal. So that was the very important point one will keep in mind while designing an ADC. For example, the conversion time for simultaneous converter. In the last session, I have discussed the simultaneous converter is very low, whereas the same for counter converter is very long. In my earlier sessions, I have discussed both the simultaneous converter and the counter type of converter. The simultaneous converter is having low conversion time, but the counter type is having long or large conversion time. And another aspect for newer designs is that multiplexing. Sometimes multiplexing is to be done in the circuit. And what is multiplexing? Multiplexing means when there are more than one inputs to the ADC, that we are calling as the multiplexing. So more than one inputs will have to be fed to the input of a circuit, sometimes for some applications. So that is called as the multiplexing. So under this condition, the most suitable ADC is the successive approximation type ADC. So this successive approximation type ADC is such a design of the circuit that allows the multiplexing. And the block diagram of this successive approximation ADC is simple as it is as shown in the figure. And here a block of the dotted line contains some circuitry that includes control logic and clock, and ring counter is there, normal counter is there, and layer amplifiers are there. So all these four components are grouped together in one thing, and that we are calling as the successive approximation resistor. So this successive approximation resistor, what it does when it performs, it stores some information in it. So that is why it is called as the resistor. And in short, this can be called as a SAR. So SAR means successive approximation resistor. And the output of this SAR is given to the ladder circuit, and the output of this actually this ladder performs or ladder forms the DAC, digital to analog converter of this successive approximation circuit. So this ladder network is needed to convert a digital signal into an analog signal, because here we have a comparator. To this comparator, two signals are fed and both are analog. So this is Vx. Vx is the input signal which is to be converted into digital, and from ladder another signal comes which is also analog. So this we can take as a reference voltage, or actually sometimes it is called as the VDAC. So VDAC or VD, or that means the output of this ladder, they can be represented as a VD or VDAC. So two signals are there, and this comparator compares these two signals and accordingly produces a differential signal, and that is fed to this control logic system. And according to the magnitude of that differential signal, this control logic works. And when the this reference voltage becomes equal to the input analog voltage, the differential signal across the output of this comparator becomes 0, and at that time this control logic stops working. And the digital output is actually taken here from the level amplifiers, and this circuit is for the 4-bit ADC, and so that's why 4 lines we have shown here, and this is the MSB and this is the LSB. And next we will see how this circuit performs. The internal structure of successive approximation register is as shown in the dotted line block, and this register does what is that instead it is a counter. Basically ring counter is also there, because ring counter is used because the input is a variable one here. The input voltage is a variable 1. So because of that reason, a ring counter is used. And this ring counter, instead of counting up in binary sequence, this SAR counts from beginning and tries all values of bits. So each time when the clock comes into the SAR, and every time it does not count in the forward way, it again comes back and starts counting from the beginning. So that means it looks for all the possible values to match with the input values. So that is how it works. So counting starts from most significant bit, which is called as a MSB, and goes to least significant bit. So this SAR looks at the comparator's output to check if the binary count is less than or greater than the analog signal input. So this comparator, so that goes on only when the input signal is greater than the output of the ladder circuit. And here we come across two types of situations, or two types of conditions, and let us discuss the working of 4-bit SAR ADC. And what are these two conditions? They are, if Vin is greater than Vd, Vin is the input voltage and Vd is the DAC voltage, or the voltage from the ladder. So if Vin is greater than Vd, next bit is set. next bit is set, and where this VD is the output of DAC. And if V in is less than VD, if V in means input voltage is less than the DAC voltage, already set bit is reset, and next bit is set. So these are the very important conditions one has to take care, and based on these two conditions, the algorithm of this successive approximation works. And suppose that if A1, A2, A3, and A4 are the 4 bits, here we can treat or we can take this A1, or we will set A1 as a MSB, the first bit, and A4 is the LSB, last bit. And when the circuit is switched on, MSB is always set 1 and all other bits are set to 0. So initially before start of the circuit, all bits will be 0. And when the circuit is switched on, the MSB set 1. Set 1 means it will be in working condition, or it goes high, and all other bits are set to 0. Set 0 means no working condition. So this algorithm is given below. So algorithm for this 4-bit DAC we have shown here, and you can see here how it works. I will explain. So start. So his signal enters here. So the clock begins, and 0, 0, 0. Before switching on the circuit, all the bits are at a 0, 0, 0 level. So when the circuit is switched on, the MSB is always set 1. This is the MSB. The MSB is always set 1, and all other bits are set to 0. And now the two possibilities comes. So that input voltage may be greater than the VDAC voltage, or it may be less than the VDAC voltage. Suppose if the input voltage is greater than the VDAC voltage, then the condition 1 applies. What is that condition? First condition, if V in is greater than VD, next bit is set. So look here. So 1, 0, 0, 0 is the initial setting of the bits, and now V in is greater than VD. Next bit used to be set. You see, this is the already set bit. This one is the already set bit, and next bit means this 0. Next bit means this 0, and this 0 becomes 1. So you are setting a bit means it is made on, so it goes to a high level. So the next bit is set 1 here. And similarly, you come down here. If V in is less than VD, what is the condition? Go back and see here. If V in is less than VD, already set bit is reset, and next bit is set. So that we can check here. Already set bit is reset. So here this 1 is there, which is MSB. MSB was set here. So that is the already set bit, that is reset. So reset means we are making it 0. That means it is switched off. So that bit is switched off. So already set bit is reset. So that is mid 0. And the next bit is set. Next bit is this second one. Second MSB it is actually. So this second MSB is set. So it becomes 1. So in this way, all we have to check. And we came here. So for this condition, the next bit is set. Next what? Again, the two cases arises. Again, the two cases arises. V in, if V in is greater than VD, if V in is greater than VD, we have to set the next bit. So here, the next bit is this one, third MSB. Third MSB, so that we have to set. So here you can see it has gone 1. That means the third MSB is set. And here, when Vn is less than Vd, already set bit should be reset. So here, this one is the second MSB is the already set bit. So that we have to reset. So that is why this goes 0. This goes 0. And set the next bit. Set the next bit means this one. This is the 0. This is the next bit. This we have to set. So it becomes 1. So it becomes 1. And this is the output. Next, we are coming here. Again, same thing. V in greater than Vd and V in less than Vd. Two conditions we have to set. So when V in is greater than Vd, we have to set the next bit. So this is the next bit that we have to set. So it has gone 1. And V in is less than Vd. So we have to reset the set bit. So this is the which bit is reset? The earlier, just earlier bit is reset, not the two earlier bit. So this is the earlier bit. So this is set here. So that is reset. That is reset. So it becomes 1. And set the next bit. So this is the next bit, last bit or 0 or LSB. So that is to be set. So it becomes 1 in this way. Next, you are here. And again, two cases. For V in greater than Vd, we have to set the next bit. But there is no next bit, as it is simply a 4-bit circuit. And this V in is less than Vd case. What we have to do? So this is the condition. So this is the last bit set. That has to be reset. So that is why this LSB becomes 0 here. So this is the last bit which was set, and now it is reset. And next what? We have to set the next bit. But to set the next bit, there is no bit, as we have only 4 bit. So you have to stop here. So similarly, same thing happens here. According to these two conditions, we have to set or reset a bit, and same procedure you follow for all these things. And what you will come to know that this algorithm, processing of algorithm stops at here. And when you look at all these binary numbers, what is seen is that these are the numbers from 0 to 15. So this 4-bit circuit of ADC supports voltage up to 15. And if any one voltage between 0 and 15 is applied to the circuit will, what it does, it analyzes all the bits so that any one bit is equal to the input voltage. So in this way, it approximates by comparing the input signal with all possible outputs of each bit. So in this way, this algorithm is processed. And it is seen from the above diagram that each conversion takes the same time and requires one conversion cycle for each bit. So here almost all, this is one conversion, this is another conversion. So for every conversion, one cycle is needed. Time equal to one cycle is needed. So that is a very important point. So it requires one cycle for each bit. So the time of one or the time period of one cycle becomes the time of conversion for each bit, so like that. And thus the total conversion time is equal to the number of bits n times the time required for one conversion cycle. So the total conversion time, how it is calculated? It is equal to the number of bits in the circuit, which is multiplied by the time required for one conversion cycle. So one conversion cycle normally requires one cycle of the clock. So as I told, one conversion normally requires one cycle of the clock for its completion. So for example, if you have a 10-bit converter, working with a 1 megahertz clock, which is working at 1 megahertz clock, has a conversion time of 10 into 10 to the power minus 6. So here what happens? 10 here, 10 is there because this is the circuit of 10-bit, and next time required for one cycle is 10 to the power minus 6, since it is a mega cycle. And because actually number of cycles, this 1 megahertz is the time period, and 1 mega is the total number of cycles present per second. This 1 megahertz. So there are 10 to the power 6 cycles are there per second. So the frequency, one cycle means the frequency becomes the reciprocal of this time period. So that is why 1 by 10 to the power 6. 1 by 10 to the power 6 becomes the time. So 10 to the power minus 6 is the time for one cycle. And so this 10 is multiplied to 10 to the power minus 6. It becomes 10 to the power minus 5. That means this we can write as a 10 microsecond. 10 microsecond. So that means a 10-bit converter. A 10-bit converter takes 10 microsecond to complete one cycle. So this is how the time is calculated in this type of circuit. So you can look at this time. It is 10 microsecond. It is very small time. So we can say that this successive ADC, this successive approximation ADC not only allows the multiplexing, but also it has a very good conversion time. The conversion time is very low, which is in terms of a microsecond. So because of this reason, this SAR ADC finds a very large number of applications. So what are the advantages of this SAR ADC? It consumes the low power. Low power consumption is the specialty of the circuit. And high resolution. This high resolution comes because you can go up to 18-bit design. Generally normally 16-bit design is normal, but with little bit more effort, you can design a circuit of 18-bit. So as you know, the number of bits, as the number of bits increases, the resolution of the circuit increases. So because of this reason, as it can goes up to 18-bit, it has the high resolution and small form factor. Small form factor. Form factor is associated with the errors in the conversion. So conversion yeah, means even though it completes it converts the analog signal to digital signal, we cannot say that it is 100%. A small correction is there. It is called as the form factor. And high accuracy. Accuracy of the conversion is also very good. And it is economical. Cost wise or the fabrication wise, it also a low cost circuit. So that can be easily constructed. So these are the advantages of SAR EDC. What are the disadvantages? Incorrect reading bar values when the noise signal is arised. So when the noise, if there is a noise signal in the circuit, then the output may not be correct. So that is the slight problem is there. And the filter can be used to reduce the noise. So in order to reduce this noise signal, filter circuit can be used. But if you are using the filter circuits, what happens? The filter circuit reduces the speed of conversion time. So that is the another problem. So that is why you have to compromise here. You have to compromise here with the speed of conversion. So if you want to reduce the noise, you have to use the filter circuit. But once you use the filter circuit, the speed reduces. So according to your need, we have to decide. And disadvantage is that as the resolution increases, the ADC slows down. Suppose that, for example, 18-bit. 18-bit design is generally having high resolution. But as the number of bits increases, the ADC goes, the speed of the ADC slows down. So that is another drawback. So if one compromises with these drawbacks, nevertheless, this SAR ADC is a very good ADC circuit, and most of the time it is used to construct the digital voltmeters, digital ammeters, all those things can be constructed easily. So this is about successive approximation ADC, and in the next session I am going to discuss the one more last ADC, which is called as which is called as the dual slope ADC. Thanks for listening.